Good. So welcome to this second to last lecture of the autonomous robotics course primarily on timing. So I will be talking about timing and coordination, and then I might talk about primitives if I get there. So in what we had so far in the vehicle dynamics, clearly, the behavior was created in closed loop. Constraint information came into the vehicle planning dynamics, the heading direction dynamics, and then it generated a time course, and then ultimately, maybe a target was reached, but there was nothing actually special about time, right? The target was reached, however long it took to get there. So time wasn't controlled. There wasn't a desire to arrive at a certain amount of time and then maybe correcting if you're running late to catch up, or if you're running ahead to slow down. And that's a good description of what people do when they walk. When you walk and you avoid an obstacle, it takes a little longer to reach a certain location, then you don't actually control, to arrive, compensate to arrive at the right time. In reaching movements, you might have similar things in reaching movements in that, there could be some online modification, like if you're reaching and avoiding an obstacle, you might take a slightly different path depending on sensory information. But generally, what we do as humans and what we do in some cases with robot arms is a little bit different. It's timed in the sense that you're planning to arrive at a particular time. And in the more advanced approaches that I will be showing you, you're really doing that in the sense of stabilizing. That is, you're compensating for delays. So for instance, when you catch something, you really try to be there at the right moment, the moment when you can interact or interface with the object. Sometimes there's also coordination among multiple effectors. For instance, humans coordinate their two hands when they operate on an object, and robots might coordinate with another robot or with a human that they coordinate with. Like shaking someone's hand actually involves subtle forms of coordination where, for instance, if the person who reaches out to you slows down with the reach, you would also slow down to still meet at the same location at then a shared time. So you don't want to maybe stay there and wait for the other hand coming. That can also happen. And things, when there's timing of this nature, then that means that you have to make changes to your plan or your control before you really reach that goal. So you have to anticipate in some way how long it's going to take to get there, so that you plan ahead to arrive in time. So that's opens a whole range of problems that need to be addressed. So my first one is to talk about that in textbook level conventional robotics, or conventional motion planning, includes time. And time is there often just an issue of planning convenience. You set a path with a desired temporal profile, for instance, and then you can make sure that the robot has a controller that it can track that path, and you could make sure that you don't design time courses of your path that are not feasible for the robot, that involve maybe some acceleration that you can't really achieve and so on. So conventionally, that's done either in joint space, or it can be done in end effector space. And that might mean that the path takes a simple form of joint space on end effector space. I don't want to rehash that issue. And more generally, even in some more abstract spaces. But what I'm driving at now is that the time course is planned by having a parametric function of time. So very often it's actually very special, like polynomial or some other forms of functions that are designed so that at a given time t, you have traversed the path from where you wanted to go. You have a scaling parameter. There's a scaling parameter that describes the time course, and you translate that scaling parameter into the path and end effector or in joint space. You can see that that would make you move along that. And you can then compute and sort of planning programs would do that, compute for you the parameters A0 to A3 that would achieve the desired arriving time and so on. And by choosing particular forms here, you can make sure that the movement is smooth, that the acceleration, for instance, has some limits, or that the acceleration is here, for instance, the initial acceleration is below a certain threshold that might be important for the controller. Yeah, I don't want to go into the details of this. This is textbook stuff. This Lynch Park textbook I might have mentioned earlier. If not, I'll give you that reference on the webpage. It's a very good textbook that introduces these sort of ideas. So there are ideas. Essentially, you can just, if you want to change the movement time, you can just rescale these profiles, and you can choose, have parameters that you can choose different things, like that you only scale the ramping up and the ramping down, and you could vary the maximum velocity that you'll have. Sometimes people have certain special techniques to round the transitions so that your velocity, doesn't have a sharp corner, so it limits the accelerations on. So these are the sort of things that play a role in this timing. And typically, well, maybe I'll say this thing before then. What you can do is you can take limits about acceleration into account. So you can define surfaces in velocity. This is velocity, phase space velocity versus the current state, and this S again is the scaling variable that expresses where you are along the trajectory, and you can express constraints about velocity as areas in this curve that, depending on your current state, that you can enter or cannot enter. So there's a whole technology how to do that. So what is not so commonly done in this way of thinking is to say, would I update that anywhere through the movement, right? This is something where you know ahead of time where you want to go, how fast you want to go there, and so on. You make a plan like this. While in autonomous robotics, of course, you would have potentially online perceptual events that modify your plan, where you would the plan, you would have complicated computation. We would have to say now that I still have so much time left, and I'm actually here, or let's say the target moved further away. How would I update that profile? That's not part of this language, right? This is more for programmed robotic timing. Okay, cursor's in the wrong spot. So in autonomous robotics, there are slightly different ideas, and ideas that are then more control-like. That is ideas where you would be able to modify on the fly the time course that you're planning. And I'll just give you a little bit of a flavor of the state of the art of that, and then I'll show you our dynamical systems versions of that. So in the literature, there is where I believe that Kotichev's juggling robot was some kind of breakthrough there. I can't be sure historically he's really the first. I don't know that exactly, but it's certainly a very good example. What he did is build a juggling robot. It was a robot that had a paddle and it would hit a ball. It was actually just keeping a ball in the air by hitting it periodically. And so that involves timing, in that you have to hit the ball at the right time, at the right place, to keep it, in good resonance, to keep it flying. There's a control problem that you need to keep the ball in a certain area, and that was, in some sense, conventional. That is, you would control the orientation of the paddle by a proportional controller, where you would see how much it deviated from the desired location along a horizontal surface, right? You want to keep it in a certain area there, and any deviation from that desired position, you would compensate by rotating the paddle to drive it back in a certain direction. But the way of keeping it moving was based on modeling the falling motion of the ball and inserting into that equation. That's the equation of free falling particle under gravity, right? And inserting into that equation a term that reflects the pedal's impact on the ball, so that the complete equation has a limit cycle so a periodic, stable periodic solution as a solution with some heuristics. And so that's an idea. So then the timing emerges from this coupling of the physics and the control signal. And that idea is used in a number of, especially in locomoting robots. So for instance, these hopping machines of Rybert have that same principle. And it's possible that Rybert invented that. I don't actually know who historically did that. So they have a similar logic that you insert actuation. Here, this leg can be extended, so make an impulse. And again, the impulse is what keeps that robot hopping. So it makes this periodic solution with a desired cycle time. And the orientation of the one leg is used to keep it in place, or to move it along a desired trajectory horizontally. And so if you generalize that, there is an idea that, again, Kodychek articulated, I think it's just a conceptual idea, that you would have a high level, meaning invariant abstract level, for instance, about where your body is in space, or where that some virtual end effector is in space. And it will be at that level that you're planning a temporal template, and you erect a dynamical system that has a periodic solution at that level. And that's called template in his case. And then the way how that is linked to your degrees of freedom is, that is a question of inverse kinematics and then forward kinematics, so that you can then actuate these individual joints to create for the relevant task level, for instance, the body position in space, the time course that you desire. So for instance, in locomotion machines, the policies you have are for moving the center of mass of the body along a certain trajectory with a periodic motion superposed. And then you're computing what you have to do at the actuator level to actually bring that about. So a lot of robot locomoting devices, biodogs or other kind of devices that use some form of idea of that. So they have a level of a virtual representation of the system at which they create the control and the time course generation, and then they couple that to the actual robot by transforming it into the actuator degrees of freedom that you have. There's also often, in many of these systems, a discrete control sequence controlled by a state machine, where you control which leg is on the ground, which leg is lifting up, so that does the coordination. And this is sort of outside the details of this movement of the individual leg. So the individual leg controls its individual dynamics independently of the other legs. It's just the initiation and termination that is then coordinated with other legs. So I wanted to show you this video, one of from this Boston Dynamics. This is the company founded by Rybert, and this is one of their dogs, robot dogs. This is like 5 years old, or a couple of years ago. The demonstration that the system is autonomously controlling its posture. So when it was mistreated like that, it would actually recover posture. It's quite impressive, right? That you can recover posture like that. And all of this is based on controlling the timing of these legs in this template anchor kind of way, that it plans a sort of a footfall, and the legs are autonomous in the sense that they can react to achieving different spatial positions. For instance, when the ground is uneven, it will not actually necessarily achieve the position that it was planning, but it would just continue in its cycle, in a sense. And the coordination among the limbs is this finite state machine. So that makes sure that there is this particular sequence of footfalls, and then it has sensors in the body that inform that system about its, for instance, balance. And those are the ones that then modify the control sent to the individual limbs to sort of like Kodychek's pedal, to make a footfall a little further out or further in to counteract that perturbation. And so this reaction to the very strong perturbation is just the effect of these various influences. There's a lot of parameters to take care of, and it's got ingenious devices. Be aware that these robots are remote controlled in terms of their navigation, the path they follow. Right? There's someone with a joystick that tells these robots where to go. And it is the locomotion part, the footstep part, that is autonomous. And it has this aspect of timing. Okay. So there's a lot of demos like that on the internet, and you will know that these are still demos. That is often difficult. You still see my presentation now, right? Or again, see my presentation, I hope.
Yes, we do.
Thanks. Thanks for your feedback here. So if you're interested in that sort of thing, you Google that. Maybe you have seen that. So that that problem of robot locomotion is very intimately connected to time. You can imagine that in a robot system, if your leg is extending too slowly, then you would be falling over to that side, and so it's not in a, you wouldn't generate the opposing momentum in time. And if you're maybe hitting the ground too early, then you would fall over in the opposite direction. So the correct timing is important to keep balance. It's one of the components of that. So to really understand that, one needs to go into that in more detail. It's actually, some of these algorithms are in public. There's a lot of know-how in these sort of ideas. So that's just sort of to give you an idea. Okay, classically you have these scores, and then dynamically, in autonomous robotics, it's much more a control-like behavior where you're updating the timing plans all the time. I will come back to this issue, and now I wanted to talk a little bit about human movement and human timing, because that gives us an opportunity to understand more better the concepts, and then we can go back to how that's used in robotics. And there are actually some branches in robotics that are related to arms, not to locomotion, where these ideas from human movement or biological time movement are used much more explicitly, including by some of my collaborators. So I'll first define a little bit again what timing is, and do that separately for relative and absolute timing, and then talk about coordination and show what the evidence is for using coupled oscillators as substrate for this timing. They are actually neural oscillators. So let's first clarify what absolute versus relative timing means. These are two time trajectories. Could think of these as some kind of activation variables. I generated that from a model. Just to illustrate the idea. So if you take any of those individual, let's say, activation traces, then you could say, what about it is timing? So for instance, you could say, well, maybe there is some threshold level. Here I always marked when the activation goes through this threshold coming from below. So here, and then again here, and here, and here, and here. And so this would be a system that makes a rhythmic, somewhat approximately rhythmic set of events, of these kind of events. Let's say each event would maybe trigger some movement, and you could say the timing of that event is reflected in the distance between these events. So these cycle times here across these different things, that would be absolute timing. So in this case, it would be very variable. It's not strictly periodic. It's very noisy. On the other hand, you could say, how are the corresponding events in these two signals aligned? So if you compare this event to that event, the first one was actually lined up to be precisely coinciding, but then you see here is the threshold event of this trace, and here the one of the other trace. So there is a certain time difference, dt, delta t perhaps, between these two events. And then a cycle later, there's again a difference, and a cycle later a difference, and so on. And you see that here, you would say that that's an expression of relative timing, right? This time difference between these would express how the events are aligned across these different activation variables. And you would say, this seems to be quite well aligned. For instance, you have a very large, long cycle, but then the cycle is long in both signals. So somehow when one signal is slower, then the other is also slower. So relative timing is stabilized perhaps in some way. And that's actually something we very commonly find. So let's first talk about absolute timing. So in human movement is general time. I'll come to that in a moment. But there are tasks where it's very apparent that your time is very important, right? In musical tasks, and you can produce a periodic signal on purpose. And you can do that without an external signal. In music, when you produce music, or you could be listening to music and tap along or dance, and then it would be important that you create a certain time structure that makes the rhythm, right? And we are actually very good at that. So the experimental task that studies that is a task in which you set this up by giving someone a metronome, and then you remove the metronome and ask people to just continue with that rhythm. You can do that very well, and when you do that, you can measure how variable your movement time is, and you find that the cycles are quite precise. So, for instance, you can do a variance smaller than about 5%. So we typically measure that in terms of the percent of the cycle time. You can do better than 5%. So that can be down to less than 50 milliseconds, maybe 30 milliseconds. For a rhythm that's about a hertz, 1 per second. You can go fast, like 300 milliseconds. So 5% of 300 milliseconds would be 15 milliseconds, right? So that's a very, very good precision that you can achieve. There's some subtle stuff about that. Maybe I think I'm on a gloss over that, so you can actually find out that there are different correlations in these signals that ultimately have to do with the fact that, if you have a particular cycle, it could be that the preceding signal was shifted or the following signal is shifted, and that will induce some correlation, because then the next cycle is going to be shorter if the previous cycle was longer. So it's an anti-correlation that is extracted in some way. And globally speaking, an important insight is that the variance of your time is in a sense in percent. You see here that when the cycle time becomes longer, the variance increases, so that you would, if you were to divide by the cycle time, it would be more or less constant. So that when you make let's say a 1 second cycle, then you have more variance than if you make a half second cycle. That's in a percent of the cycle time. That's the main fact to explain. And so theoretically, we're talking about periodic signals, then we're really talking about oscillators, right? I don't know if you realize that the thing that we call clocks are actually oscillators, right? It's in the mechanical grandfather clock is an oscillator. It's a sustained oscillator, or stable oscillator that small perturbations are reduced. System will reapproach the rhythmic solution. This is what we call a limit cycle oscillator. It's the generalization of a fixed point attractor. It's a periodic attractor. There is a mathematical theory of clocks that amounts to accounting for them as limit cycle oscillators. So very developed in the Soviet Union. Antonov and Witt is a famous textbook that studies the mathematical modeling of clocks. And the modern electronic watches are very much like that. They have a self-excited oscillation and then electronic oscillation that then very high frequency that then keeps adding up time, and that's the basis for time measurement. So mathematically, limit cycles are just a mild generalization of the fixed points that we have. I think in my mathematical tutorial, I briefly showed you the Hopf normal form. That's a bifurcation from a fixed point to a limit cycle. So a limit cycle can be written as a periodic solution. So written in this form where omega dot is, phi dot is omega. So phi would be omega times t plus a constant. So this was cosinus of omega t. So it's an oscillation. And the amplitude of that oscillation emerges from something like a pitchfork bifurcation. So if you have a sufficiently positive coefficient alpha here, then you would get a fixed point that is stable at a non-zero radius. R is the radius or amplitude of that oscillation. And the phase would just always keep growing. So that's the prototype of a limit cycle. Now, in practice, the models that account for clocks vary. For instance, grandfather clocks are not as harmonic as these. They don't have sinusoidal solutions. Neural dynamics tend to create time courses that are more like grandfather clocks, namely where there is a particular point when the nonlinearity engages. So this is the generic Amari oscillator, as we call that. It's a two-layer neural dynamics where the activation level has some self-excitation and is inhibited by an inhibitory variable, which is excited by the exciter variable. And this sort of paired excitation inhibition system tends to oscillate. Could be the basis for epilepsy and things like that. Epilepsy, sorry. And that could be is a general mathematical model of periodic activity that is actually at the basis of movement generation. I will briefly hint at that a little later. Maybe I'm not sure I do much about that in this lecture, but we work actually actively on modeling movement generation through oscillators like that. And models like that can actually account for that law that the variance of the cycle time increases with the cycle time, and some details around that. So that's as much as I want to say about that. So we are, as humans, we're very tuned to that. And actually a lot of animals, so they, on many time scales, they're very tuned to predict events in time, make movements that are, whose timing is controlled. Now, very often this fact is demonstrated through relative timing, the fact that we can coordinate movement. So for instance, when you locomotive, obviously you're coordinating left-right movement. It's a bipedal, right? It's very critical, if not you fall over. And then if you have more legs, there are more temporal relationships to control. It's also true within a limb, right? If you have a limb, then the different joints in the limb or the different muscles must keep particular timing relationships invariant for the trajectory of, let's say, the hand in space, performing a smooth, reproducible movement. Imagine the temporal coordination in speaking, right? All the different articulators must be aligned correctly so that when you're, when you make the voicing event here, that the bilabial closure is just right to make a bow or a pa or whatever it is. And mastication, when you chew, you have to move stuff around with your tongue and your mandibles in a coordinated way. Sometimes that can misfire and you bite your tongue, for instance. And that's why speaking and eating at the same time is a challenge, because then you have more constraints for that. And of course, we very often think of coordination in music production, with different fingers and, or one hand and the other hand when you're have to hit the guitar at the right moment, just when you have the right position with your fingering hand and so on. These are all tasks that are approximately rhythmic or periodic. Even speaking is quite periodic, but you can also actually have discrete acts, meaning in the sense of just happening once, that have an aspect of coordination like that. So for instance, when you're reaching, then to reach, you have one component is your transport of your hand toward the object you reach, and then you open and close your hand to grasp the object. And these two are coordinated. You observe, for instance, that if you're reaching for an object and then while you're reaching, you remove the object a little bit, like in a virtual reality setup. And then people will, extend the movement to reach for this shifted target. And what you find is that then they also slow down the opening so that the relationship between transport and opening is the same. Even though theoretically they could just keep opening and then approach the object with the open hand, it's actually coordinated. That is, you're slowing down your opening movement as you're slowing down, or as effectively the movement to the target is slowed down by the target moving away. It's a famous example of the coordination that is just inherently there. It isn't functionally necessary. The robot that you program could reach the target successfully without having that coordination. When you handle object with two hands, you're clearly coordinating that way. When you grasp, you coordinate, to stabilize the grasp, and there's very fine control over that. If you accelerate an object, then you would increase your pressure on both ends to stabilize the grasp. And then catching, intercepting would be examples of discrete coordination. So coordination is, strictly speaking, really the maintenance of a stable relative timing, stable timing relationships between the components of the movement, and maintenance in the sense that when you're perturbed either by external events or you're perturbed maybe by neural noise, then you recover from that perturbation, you compensate for it. There's a famous example in speech articulatory experiments where you look at how the speech apparatus reacts to perturbation. So in this experiment, for instance, one version of that experiment, you would actually pull down the jaw by having inserted some device that's mounted on a motor. I was a participant in one of those experiments where they pull down your jaw while you're speaking. Or there could be a perturbation just of your lip, like a little stick that's can pull your lip down while you're speaking. It's a motor, and you can control when it's pulled down. And there you find, for instance, that there are reactions to these perturbations that reinstate the correct timing. There's actually also spatial aspects to that. So a famous story about that is that it really depends on your articulatory goal. So for instance, when you say in the experiment, it's a bob, again, it's a bob, 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 you know, that being there you need bilabial closure to achieve the b sound. And if you pull down the lip, then you will see compensation. For instance, you will see that the upper lip comes down to meet the lower lip and make that closure, something that you can't even voluntarily do. While if you say it's a baz, no, that doesn't require bilabial closure, then you don't see that compensation. So it's really a very functionally specific form of stabilization. Now, that's not actually stabilization of timing, but there are variants of that I can't explain in detail that actually really show that you're making a compensatory change to achieve the temporal alignment of the different events that then lead to the articulatory event, which is usually, you know, the generation of a consonant or of a vowel. And another form of coordination is, of course, if you stabilize the timing relationship between an action and a perceived event in the world, like catching is like that, right? Where you make sure that your hand is at the right spot at the right time, and as maybe some perception, like a wind gust, you know, accelerates the ball, then you would be compensating for that. There's a lot of studies about us being able to do that, and we are very good at that. So you could think, is it trivial? Is it natural that that would happen? I already said initially, no. There are, locomotion is the most famous example. When you walk, you don't always control that you arrive at a given time. You don't always compensate for lost time or for being ahead. But you can, for instance, when you run to catch a ball, you are coordinating your running speed to arrive at the right time. Still, this is a sort of a special system. Navigation is very different, while pretty much all the upper limb movements in humans are timed, coordinated, and you coordinate them spontaneously, even if you don't need to, as I just said. Here's a little story that goes back to my initial entry into this field that is kind of illustrative. So very often you find that there are two patterns of coordination that arise spontaneously. So one is in phase. So you're moving two homologous limbs at the same, to be aligned in time. So for instance, these fingers are like that. If you play piano, you might have a tendency to coordinate. If you drum, you might have drumming, actually, this would be in phase for drumming. So a gallop, for instance, has some approximate in phase for the two limbs, front limbs or hind limbs, while the other would be anti-phase, so alternation, right? So this would be, for instance, anti-phase, right? Going up versus down. And you also find that in a lot of places. So in for instance, synchronizing with a metronome, anti-phase would be syncopation, where you go off the beat. So whenever the beat comes, so you tap between the beats, right? And then your sound perception and the movement is an anti-phase called syncopation. And the trot would involve, for instance, anti-phase, right? The two limbs alternate. So these are patterns that with many effectors you can produce spontaneously. And there's an interesting phenomenon discovered by Scott Kelso, with whom I worked as a postdoc. It's a phenomenon that anti-phase tends to be less stable. So if you have an anti-phase pattern and you try to do it very fast, then you will sometimes fail to do it at high speeds and then switch to in phase. So he did a lot of experiments, and this is from a summary of some of those experiments where that switch was observed. So for instance, here, these two muscles this kind of movement was done because the muscles are easy to record from. And there you have initially alternation, right? This muscle alternates with that muscle, and then there's something happening, and then they are aligned. So then they switches to in phase. So this would be antiphase, and then it switches into in phase, particular to homologous muscles co-contracting at high speeds. Or you stop, but you have to, if your task is to make that high frequency by a metronome, for instance, then you have that tendency. So that's a curious phenomenon. The antiphase is more related to inhibition, because one muscle the neurons that drive one muscle will prevent the neurons driving the other muscle to fire, while as in phase is mediated by excitatory coupling, where they tend to fire at the same time. So there's some kind of intuition, perhaps, that inhibition makes things unstable. Not entirely clear why that's the case, but one could perhaps think that. But the point about that is interesting is that when the antiphase becomes unstable, literally, it is an instability. And Scott Kessler made this experiment, so let's switch to text, where he had people start out in antiphase. You see these dashed lines are from one limb, from one finger, and the solid from the other. And you see the event times here. They're alternating, and then at higher frequencies, they switch into being synchronous. You can compute something like a relative phase, where you compute, for instance, the distance between these two events divided by the cycle time. Then it will be about 50% or 0.5 here, and then switches to 0, which is the same as 1 here in phase. So it's a periodic variable. There are multiple ways of assessing that. And so the interesting thing when you do that is that you find that some indices of stability reflect how far you are from the decision. So for instance, if you just look at the variance from time to time, from cycle to cycle of relative phase, for instance, then that's a measure of the degree of stability. More variance, less stability, right? You know that from the dynamics tutorial. And so what you observe is, I'll show you, you observe that variance increases before the instability. Another measure is relaxation time, the time you need to recover from a perturbation. So if you're less stable, you need a longer time to recover from perturbation. That was actually really done in this experiment. So you actually perturbed, here is some traces of the fingers, and this is the velocity, and this is a particular form of relative phase. And there's a torque pulse coming into one of these fingers that perturbs the finger here enough to be shifted in phase. And then it takes some time before the fingers find back to their root. You see, it takes about a second and 300 milliseconds before we're back here to the original picture. There's some criteria that you use to determine that. And this is the same in the in-phase pattern. You see that here it returns more quickly to the unperturbed pattern. You can see that with the naked eye, that here this is a small window, while here it's a longer window until you're back. And so that time measured in some way would be an index of stability. And you, roughly speaking, find that variance increases as you approach the frequency at which you transition, and relaxation time increases. Here are some data examples. This is relaxation time for individuals. A very strong increase in the antiphase is the open triangle, while the in-phase is the filled triangle and just goes through constantly. And subtle here that at higher frequencies, your cycle time is shorter, and that makes it actually easier to detect fast transitions. So if anything, the measurement bias is in the opposite direction. So it's quite a clear and strong piece of evidence for slower reaction to perturbations. And similar for variance is the effect for variance across many participants. Very strong effect. It's like a factor of 2 more variance here, and none in the in-phase pattern. So the notion that was developed around that time was that individual movement processes could be characterized by a neural oscillator that makes the timing, and that their coupling leads to in-phase. to stable relative phases. Excitatory coupling tends to lead to in-phase and inhibitory to anti-phase. Here is a example of a concrete model like that. So it would really show up in the other neuron showing up in the equation of the first neuron and vice versa. And there can be different forms of coupling. And so that would mean that if one of these systems lies ahead, it then is pulled back and decelerated to be aligned, and also vice versa, that the first is accelerated to be aligned. You will find these kind of solutions. And I don't want to talk about this here. And from these kind of models, you would predict that a transition is an instability. That is, what happens in a transition is that the antiphase pattern becomes unstable. You can see this would be the dynamics of relative phase. The rate of change of relative phase against relative phase would become a flat dynamics, and that would predict this. There's indices of stability, and then you would be switching to the other state beyond that, that bifurcation. And so you would predict that variance would increase. I think in the tutorial I already talked about that, right? You have a flatter slope here. The flatter slope means the same amount of noise moves the dynamics effectively more, so the attractors move more, and you therefore get more variance than if you have the same amount of noise for a steeper and more stable dynamics. Then the attractor moves less, and that induces less variance. And similar for relaxation time, when you have a flatter dynamics, then the same perturbation that pushes you to a certain distance will encounter less restoring force. It take longer to be restored than if you have a steeper dynamic, so more stable dynamics. So that's a genetic prediction. So in other words, the observation of these predicted signatures of instability are a form of evidence for that concept, that the time movements are generated by oscillators, and coupling them accounts for coordination. And there's a whole wealth of literature in this direction. So that's sort of the core idea. And you saw in this early example, there was already a little hint of that. These locomotion robots isn't quite true, because in these legged locomotion examples, the individual time course is actually generated independently for every limb, and it's actually only the initiation and termination that is coordinated through this finite state machine. So it's not exactly this kind of idea. So we've actually been trying to take these ideas more seriously in a more refined way. So many years ago, I did some work with a student, Christina Santos, on controlling a gripper to interact with an object. So this is just simulation. This is a robot arm folded initially, and then unfolding to try to meet the moving object in a particular plane. The system has a model of the movement of this object and can plan to move it in the plane. And what it has to control is its timing. So there are, again, two aspects, namely initiating and terminating the movement, which is done through some sort of neural dynamics. These terms here, U final, U Hopf, and U init, are different dynamical states of that system. So it would be moving when this Hopf term is on, and not moving when this or that term are on. But then also the time course itself would be continuously linked to some sensor information. And that link, so this the discrete activation and so on, that link would be through some measure of the time course of the approaching object. And so here I'm just saying this works. That is, the system can intercept the object. This best demonstrated perhaps here, where we're inducing perturbations, or the estimate of the time that we need to get there. So the time to contact is artificially made noisy, and the system compensates for that. For instance, here is even tempted to switch back to another state, compensates for that to still make the impact at the right location. We actually did a vehicle version of this a couple of years later. So this is a vehicle, this is just a snapshot of a vehicle that goes to a target in a certain given time. And when it avoids an obstacle, it really does try to arrive at the same time. So it does try to catch up, because it takes longer to go through this obstacle course. We're accelerating the system. So for instance, in the phase plot, the system would, without perturbation, just go along this path. So that will be the green solution. But when you then make the system move a longer path because of the obstacle avoidance, we arranged that it would update its plan so that it still arrives at the final position at the same time, approximately. So it has compensated for that loss by going faster to catch up, to still be at this larger distance at the same time. It turned out to be quite complicated to get that. There will be limits, of course, because you have a maximum speed or maximum acceleration that can do. These kind of ideas, these were very simple simulated models, even though we implemented that on a vehicle, but it is simple in terms of the robotic performance. There are people, especially Aude Billard in Lausanne, who really push this far. So she has a robot that can catch a tumbling object. And so that entails many more things than just that. Timing is a server for all the kinds of things you have. You have to have a good perceptual system, of course, that predicts where and how, in which pose you can capture that object. And some of the parameters for that are learned by observing a lot of these tumbling objects. And then you have to have a good controller that actually achieves the reach within a defined time. And so then you can determine at which time you should initiate that movement into what. And within that sort of thought, there is an idea, I'm not going to explain the detail of that, but essentially the idea is that if you couple different components of this process, so the components that observe and estimate the ball's motion or the object's motion, and the processes that govern your movement generation. If you couple them, then if there's a perturbation visual that the ball is reflected or something, then you compensate for that. And if you don't couple them, then you don't. Then you can't actually, the uncoupled case, would not actually compensate for a perturbation here of the object, for instance. And there is another video. I wonder if this now works immediately. If I go back, I have to. I hope this still works. I didn't try that before. Yeah, this is from Lausanne. It's quite impressive.
We teach a robot how to predict a moving object.
We don't need the discourse here. This is what would be.
And for that, those that can adapt rapidly to changes. Of course, this controller can be used for many different applications.
She originally worked on human-like
catching people that are in danger of falling.
And let's see the robot again. I think it was just at the beginning that we see this very cool action.
We teach a robot how.
You saw that video?
Yes, we can see that.
Yeah, right. And so that's a cool project. It was quite very well. A lot of people like that. She just published a book about these things. Very nice. So a lot of things have to be right in order to do this. Not just the timing, but the timing is the core of it. You see, it was able to even grasp objects that are soft. It's not like it works every time. There is some uncertainty in that catch. So we did a very primitive version of that a little earlier. We had not such a cool robot. This is our old robot, which was really not very good in terms of its control. And so that instead of catching, we had a ball rolled down the slope, so it was moving slowly, and we're just trying to hit it. And it used these same ideas. I'm not explaining all these ideas. It's using the Hopf oscillator, and it is updating the timing of that oscillator, and has a sophisticated neural network to control its sequencing. And so the core idea of this was that it would predict a time to contact. So for instance, when it observes the ball, it has a Kalman filter to predict where it would be along the horizontal. We're always catching it in a particular vertical direction, a particular place on the table, but where it will be along the horizontal and what time. and the pedal would then move toward that and then make this movement here, which is the pedal hitting movement. But it will be continuously coupled so that if the ball is deflected, like here going through against an obstacle, is deflected, then the pedal would update from this unperturbed to the perturbed location. And that worked. Here's an example. And you see it's making this correction. See, it's not so impressive because everything is slow. It's just slow because this robot arm isn't very performative. Our dynamics was actually working much faster than that. But it's just sort of this core principle is analogous to the one Aude Billard used. So we did this earlier, and in some sense, this is the predecessor of that previous work. But hers is much more complex and does many more things. And then we actually also had a case where the system could actually make new decisions. So here's a case where through multiple reflections, the system actually initial thinks, like in this case, that it wouldn't actually come back. So it goes to catch this here and then goes back to its base position and then initiates a new reach. And here's a demo of that. Goes back to base and then initiates a new reach. So this is, so I already hinted that in autonomous robotics, the timing needs to be updatable, right? Be coupled to external devices. So in locomotion, you saw that, because they're hitting the ground, and in intercepting objects, you have that problem. And therefore, this notion of having oscillators, even oscillators that make a single cycle, right? I didn't explain that well, that these discrete, when I intercept something, it's not a periodic movement, it's a single movement, but it is an oscillator that's just turned off after one cycle. I didn't explain that well. It's the same idea that the coupling then of these oscillators, even if they're doing a single cycle, assure the coordination of the movement. So that is sort of the main result in autonomous movement generation, to create the timing in this way. And I was going to now lecture about movement primitives in a particular way. Let me skip this and end this first part of the lecture here.